Hello and welcome to our discussion on galaxies. We're going to talk about specific types of galaxies, their basic structure, and compare and contrast with our own galaxy, the Milky Way. Now, the history of galaxies is sort of similar to what we went over with the Milky Way. And of course, Galileo was the first to realize that the faint band of light that we call the Milky Way was actually part of a much larger collection of stars. But it wasn't until much later that with Shapley and others that we were able to map the Milky Way and realize the overall extent of its structure. Now, going back to galaxies, even before we realized what the Milky Way was, astronomers began to suspect that special fuzzy patches of light in the sky, what we call spiral nebula, were actually much larger collections of stars than we realized. Now, William Herschel was the one who developed a crude model for the Milky Way, and basically got the idea that we were in this sort of island of stars. But it was later on William Parsons who built an even larger telescope than than Herschel. Getting ahead of myself here. And the 72-inch reflector that he built in Ireland was the largest of its kind. And Parsons, although he was a rich nobleman, was also a very accomplished astronomer. He made quite a few observations, quite a few drawings. And this shows you one of the drawings of the Whirlpool Galaxy. This is one of our nearest neighbors. It's not quite in the local group, I believe, but it's close enough to be able to see it with a good-sized telescope. And Parsons' sketches of this structure started to get people to wonder what exactly they were. Now, Harlow Shapley, once again, going back to the previous chapter, was able to use measurements of periodic stars, what we call R Lyrae stars, and was able to determine that the Milky Way was approximately 75,000 light years or 100,000 light years across. Because of this huge size, he believed that this was basically the entire universe. He couldn't imagine anything bigger. But a rival of Shapley by the name of Herbert Curtis thought that the universe extended beyond the edges of the Milky Way, and that these spiral nebula that the likes of William Parsons had observed might be islands just like our own Milky Way. The interesting thing about the debate that they had, and it was a very civil debate, they had this in 1920, is Harlow Shapley was right about the data that he had taken in terms of the size of the Milky Way. Curtis thought that the Milky Way was much smaller. So Shapley came up with the incorrect conclusion based on the correct data, where Curtis came up with the correct conclusion based on flawed data. Imagine that. So now we get to Hubble. Edwin Hubble, using the very large Hooker telescope, the largest of its time, ended the great debate between Curtis and Shapley by observing Cepheid variables in these spiral nebula, in these galaxies. And he was able to determine that the distances to these galaxies were much greater than the actual dimensions of our own Milky Way. I believe he measured the Cepheid variables in nearby galaxies like the Andromeda Galaxy. And although our own Milky Way was about 100,000 light years across, he was getting distances in the millions of light years to the nearest galaxies. Now, in classifying galaxies, Hubble was one of the first to do so, and his classification system still exists today. However, his theories about how galaxies change over time has been shown not to be true. And there are three basic types of galaxies that we have according to their shapes. We have the most common, which is the spiral, just like our own Milky Way galaxy. This galaxy has a large nuclear bulge surrounded by a disk of gas and dust. The disk has spiral arms of new forming stars, and that's why we see these structures from a distance appear to be these spirals. The other most common type of galaxy is the elliptical, and then we have galaxies that sort of don't fall in either of these categories. They don't have enough structure to be considered either spiral or elliptical. Now, starting with the spiral galaxy. Again, the spiral galaxy is the most common type of galaxy known. We feel that probably about 60% of all galaxies are this type. And the spiral galaxies basically have the same structure as our own Milky Way. Again, a central nucleus, a nuclear bulge, surrounded by the spiral arms, and then finally a vast halo. All galaxies are believed to have a central black hole. And what's interesting is that we found that either the size of the elliptical galaxies or the size of the nuclear bulge are directly proportional to the black hole. The question becomes is, when this nuclear bulge formed, was the black hole already there and that therefore determined the size of the nuclear bulge? Or because of the size of the nuclear bulge, a very large black hole condensed in the center? Now, look at the shapes of spiral galaxies. We basically have two types of shapes based on what the nuclear bulge does. A normal spiral galaxy has just this spheroidal bulge at the center, whereas a barred spiral galaxy actually has a bar or an elongated nuclear bulge at the center, like our own Milky Way. And the normal convention is to use S for normal spiral and SB for a barred spiral. Now, in addition to that, there are also subcategories that we place them according to how large the nuclear bulge is. If the nuclear bulge is very large, we call it an SA galaxy. If the nuclear bulge is medium size, it's SB. And if the nuclear bulge is very small, it's SC. There's an additional category called SD, which has nothing to do with the nuclear bulge. And these are basically very small spiral galaxies. We call it dwarf spiral galaxies. Now, here's a classic look at a spiral galaxy. This is a Whirlpool Galaxy. And the interesting thing is you have the main galaxy here. You actually have a satellite galaxy here. This is a very famous galaxy. Again, this is what Lord Ross had, William Parsons had drawn. And as we discussed with the Milky Way, we believe the spiral arms that these galaxies get are due to spiral density waves, which are driven through star formation. That these waves go through and they compress the gas, creating new stars, and the new stars in turn go supernova after a certain amount of time, pushing the spiral waves forward. Now, there's some interesting variations to spiral galaxies. Galaxies are like snowflakes. There's no two identical ones. And some spiral galaxies contain ring structures. And in this spiral galaxy, we can actually see a fairly nice ring right about here. And then from that ring, we have the different spiral arms that are coming off of that. Now, the source of the ring is not well understood. However, we think that in some cases this might be caused by collisions here's an interesting galaxy to look at called Hoax Object, and we think that another galaxy, probably a very compact galaxy, went right through the center of this galaxy. That's not what you see at the center now, that's the nuclear bulge. Disrupted it, and just like throwing a pebble on a pond, created these ripples that disrupted the disk. Now again, spiral galaxies do have star formation going on. And if we look at spiral galaxies using infrared telescopes and using ultraviolet telescopes, we can see a lot of molecular clouds in the disk in the infrared. That's what we see right here. But we can also see in the ultraviolet very hot young stars forming. Now here's just a few examples of different barred spiral galaxies. Just like the normal spiral galaxies, the nuclear bulge, the size compared to the disk, is used for these subsets A, B, and C. And as we can see here, an SB small a has a very large barred nuclear bulge, SBB, a moderate size, and SBC, a very small barred nuclear bulge. And again, we think that the Milky Way is probably an SBB. This is an artist's rendition of what we think the Milky Way looks like. It definitely has that central bar right in the center. Just some more examples of barred spiral galaxies. So, spiral galaxy is the most common type of galaxy, like our own Milky Way. Now, elliptical galaxies are less common, and we think that about 10 to 15% of all galaxies are this type. One way of thinking of an elliptical galaxy is it's almost like a spiral galaxy without the disk. The nuclear bulge of a spiral galaxy has a structure very similar to an elliptical galaxy. Now, the elliptical galaxies are probably formed through the merger of other spiral galaxies or other galaxies of similar size. These elliptical galaxies are primarily composed of population 2 stars, so they tend to be made of very old stars. It's almost like all the gas and dust has been used up, and all the stars that will ever form have been formed for the most part. Now, the interesting thing is, although the elliptical galaxy is made out of older stars and the spiral galaxy does contain newer stars in the disk, both types of galaxies are thought to have formed at the same time. Hubble thought that galaxies started as ellipticals, and over time they became either normal spirals or barred spirals. We think that just the opposite happens, that many galaxies start out as spiral galaxies, and as they emerge, they actually go the other way. They become elliptical galaxies. Now, elliptical galaxies are also classified according to the shape. We can't really tell if galaxies edge on to us, or if we're looking down the long axis, but we rate them according to the shape. How do they appear from our perspective? If they appear to be perfectly spherical, we call them E0s. If we find that their long axis is about twice as long as their short axis, we call them E5s. And of course, the most elongated type of elliptical galaxy would probably go out to about E7, where this numbering